I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students, and just pray that you'd bless this class. Just guide my thoughts today, Lord. In your name I pray. Amen. Okay, so this is lecture 35 by my count. And what I want to do today is try to wrap up our discussion of Euclidean domains, PIDs, and UFDs. And then I want to look at applications of abstract algebra to number theory. Roughly speaking, that's my idea for today. Now, so first things first, there was one last remaining tidbit, and I really should write a definition for you guys, so I'm going to do that. Definition: an integral domain R I'll call R is a Euclidean domain all right if it has a division algorithm let me kind of break that down. In particular, there exists delta, which goes from the ring I'll try to follow Nicholson. I think he says he removes 0 from the ring and he maps to the natural numbers such that A not equal to 0, B not equal to 0 implies that he calls this the divisor function of AB is greater than or equal to the divisor function of A. Moreover, and so he has these in 2 different pages. So what I'm doing is I'm collecting together his definition of a division algorithm and also a divisor function in one place, because you need both of those things to have a Euclidean domain. So when I say division algorithm, what I'm saying is that you can use the divisor function, in particular, given A and B, which is non-zero. Well, let's say A and D in the ring with B non-zero, okay? To be more precise, make sure we understand each other. Then there exists what? There exists Q and R in the ring such that A is equal to BQ plus R, right? And either R is equal to 0 or the divisor function of R is less than the divisor function of B. Right? So I more or less said this last time, but I used different words, right? We started talking about this concept, I think, with what I've called a norm in here, like your exercise 21 explored, right? And certainly you can use a norm to build a divisor function, right? I'm not particularly interested in the interplay between these different terminologies. I just want to pick one to use. So we'll use this, all right? Anyway, division algorithm. So the theorem that we have yet to prove, and it's kind of the final chapter in the series of thoughts we've been collecting. So this is theorem 3.7.10 in my 2016 notes. All right. Is as follows. Every Euclidean domain is a PID. What's a PID? Yeah, principal ideal domain. All right. So we should look at the proof of this. All right, so here's the proof. Suppose that R is a Euclidean domain, right? And let I not equal to 0, all right, be an ideal in R. All right, what's our goal? So it's principal? Right. So how do we get at that? Construct S, and so S is going to be equal to x in the I, such that x is not equal to 0 and, delta of x rather, such that x is not 0 and x is in I. So here, I assume delta is the divisor function for R, as is guaranteed to us by the definition of Euclidean domain. All right? Now, to be clear, I'm using n in the sense 1, 2, 3. Oh, man. Stupid Nicholson. Yes. I'm going to insist that it be there. All right. 1, 2, 3. Point is, then this is what? It's a subset of the natural numbers, right? So by the well-ordering principle, what? Yeah, there exists, x naught in I with x naught not equal to 0, such that delta of x naught, right, is less than or equal to delta of x for all x in I, right? Well, let's take 0 out of the picture. Yeah. See, this is the frustration for me, guys. It's like he has, as I understand his definition, he doesn't allow the divisor function to take 0. But a lot of times, I want to think about the divisor function of 0. I want to say the divisor function of 0 is 0. So, like, there's something awkward about his definition in my taste, but I'll try to set it aside. Let's forge ahead. It's not interesting what I'm talking about. So, we have this x naught. Then what can we do? Let z be an element of I, right? And then apply the division algorithm. With respect to what? X naught, yeah. To find Q and R in I. Well, not in I. Yeah. I'm sorry. Not in I, but where? In R, right? Such that what? Z is equal to Qx naught plus R, and either R is equal to 0, or the divisor function of R is less than the divisor function of x naught, right? Of course, by construction of x naught, what can we say?
R equals 0.
Right. r equals 0 as delta of r less than delta of x naught impossible, right? By construction. It's the smallest element. So if r is equal to 0, what do we have? Hence, z is equal to qx naught, right? But more than that, you might notice that qx naught is an element of what?
Principal ideal generated by x naught.
True. Let's see here. I'm trying to think. Do I even need that? I mean, I mean, we have that's an I again, right? Because x naught is in the ideal. So a ring multiple of something in the ideal is again in the ideal. So qx naught is an element of I. You know, whatever. That's already clear from. I'm sorry. I had a slightly different argument in the notes, and it's messing with me. So, but this is. But you're right. What you said, Zach, was good. But this is, of course, an element which implies that z is an element of what? The ideal generated by x naught, right? So, but z was an arbitrary element of the ideal, right? So that implies that I is a subset of the principal ideal generated by x naught. What about the other direction? Can we argue that the principal ideal generated by x naught has to be a subset of I? What's that? Yeah. So you guys, if it's pretty straightforward, you can tell me why, right?
Well, that's with the ideal argument, because x naught is in I, so you can multiply that by any ring element, and then you're back in I.
Since x naught in I implies that x naught times r is an I for all r in R, right? So therefore, x naught r. Well, anyway, let me stop. So what have we shown? We've shown that the ideal I is generated by x naught, which proves what? An arbitrary ideal in this Euclidean domain is principal, right? Thus, R is a PID. So let's collect our thoughts. What are the big ideas we have here? We have Euclidean domain, right? We just proved Euclidean domain implies what? Principal ideal domain. Right? Last time, we proved principal ideal domain implies unique factorization domain, right? By the ascending chain condition. So we have this chain of implications. None of them can be reversed, all right? So to show you that they're not reversible, let me give you examples. So to prove that this arrow cannot be reversed, it suffices to give one counterexample. A good example of that would be if you look at z adjoin x, polynomials with integer coefficients, you can prove, in fact, that this is a unique factorization domain. I think that is in the book. I don't think I've actually proved that in here, right? But, however, there exist ideals in z of x which are not principal. Can you guys tell me one? So I equal to what? So the ideal generated by 2 and x? Is that it? No.
Well,
That can't be it.
like 2zx and 3zx and 5zx, like all the primes. I don't know if it's true.
I think if we look at things of the form, I'm trying to remember what it is. It's something like a plus f of x, such that a is in 2z and f of x is in zx. I think that forms an ideal. So what that would be, oh, that's not quite right either. F of 0 equal to 0. What I'm trying to say is the constant coefficients are even. So you have like even constants plus arbitrary polynomials. If you add 2 of those together, you get another such thing. If you multiply that by anything, whether the constant is even or odd, even times even gives you even. So you can prove that this is an ideal, but it's not principal. To prove that is not. No. Adding. Only the constant coefficients are even. Yeah.
Well, then a times f of x would be principal.
Yeah, I mean, a times f of x might be. Well, that I think could be.
That would be the whole range. It's principal generated by
Yeah.
by the constant.
In any event, this is a counterexample. All right. I mean, I don't want to try to say what are the principal ideals in this ring. I mean, there are lots of principal ideals in any ring, right? But the question is, are all the ideals principal? If there's even one that's not, then game over. It's not a principal ideal domain. This one here is not as easy. I think what we have is z adjoin 1/2 of 1 plus the square root of minus 19, I believe it is a principal ideal domain in which there does not exist a Euclidean. It's not a Euclidean domain. There you can't construct a division algorithm in this thing. This is a PID, which forbids construction of delta with division algorithm. Now, this is not something I will explain to you, but this was shown in 1949 by a fellow named Mott, M-O-T, Z-K-I-N. There's a reference in your textbook and a footnote, along with a couple of more recent publications, which probably are trying to make that more readable or something. I also, in my 2016 notes, have links to a couple answers in the Math Stack Exchange, which give you other examples. This is not an easy thing to illustrate. But in fact, that is also not reversible. That said, many of the examples we're interested in are Euclidean domains, and so we often have that technology to work with. All right? So that's kind of the big last hurrah in this course in terms of theory, which is this story here. There are a few more things I want to tell you, but that's one of the big ones. So now I'm going to turn to looking at some applications, all right, of abstract algebra. Start with something relatively benign, which actually doesn't involve this story much at all, but I think it's something that's worth pointing out because it's kind of neat. And I don't know if I talked about it in here yet. Have I talked to you guys about the two-square identity? I don't think I have. So the two-square identity, what's it say? It says that a1 squared plus b1 squared times a2 squared plus b2 squared is equal to something over here. All right? Now, let me show you how to do it. Let's think of these as, let's think about a1, and you know what? This a1, b1, a2, b2 is annoying. Let's do a, b, c, d instead. How about that? That's easier to write, isn't it? Let's do a, b, c, d. Okay? I want to think about a, b, c, d as integers. A, B, C, D, and Z. So what I'm going to do is I'm going to use the Gaussian integers to say something about integers. So if I use Gaussian integers, what can I write these as? I can write this as a plus IB times a minus IB, right? This is C plus ID times C minus ID. So over the Gaussian integers, these factors like that, right? And so you can do what? Then this is also, and maybe it's even better to say that this is Z bar times W bar, right? Where Z is equal to A plus IB and W is equal to C plus ID. But we know properties of complex conjugate. How does it work? That's ZW times ZW bar, right? So this is really just the modulus of ZW squared. Well, what is ZW? So that's AC minus BD plus I times BC plus AD, modulus of that, which is AC minus BD quantity squared plus BC plus AD quantity squared. And that, folks, is the two-square identity. It says that the product of the sum of squares, sum of two squares with another sum of two squares, is yet again the sum of two squares. Now, that's a statement about integers, right? That's a statement about counting numbers. And yet, how did we prove it? We proved it using Gaussian integers. This is sneaky, right? Now, this identity has been known a lot longer than Gaussian integers was known, but it's kind of fun to just appreciate what it does for you. Let me show you an application of this. Let's see here. So, sorry, I'm trying to look at a good example. Excuse me. Let's see here. What if we did something like, let's just see what it says. If we do 3 squared plus 1 squared times 2 squared my d, and so, I mean, this is what? This is 10 times what? Is that 13? So this is 130 then, huh? So we're trying to write 130 as a sum of two squares. And it's going to, it's going to be this. What's that? A times C, which is 9 times 4, minus B times D, which is 9. 3 times what? Oh, I'm sorry, I can't keep my, so it's 3 times 2. Is that minus B times D? This is 3, isn't it? Plus then what? Squared. BC is 2 plus AD is 9, right? So what's that give us? That gives us, so that's 3 squared plus 11 squared? Well, of course. So 9 plus 121, 130. But it's kind of neat, right? And if you study this, if you have a Pythagorean triple, right? In other words, what's a Pythagorean triple? If we have A, B, C, right, such that what? A squared plus B squared equals to C squared, then that's a Pythagorean triple. A corollary to this two-square identity is the following. If you have A1, B1, C1, and A2, C2, A2, B2, C2, Pythagorean triples, right, then what else is a Pythagorean triple? Right? I mean, so you do, well, let me just copy it down wrong. So A1, A2 minus B1, B2, comma, A1, B2 plus B, A2, B1, I think. And then, what is it? What do these square to? C1, C2? Yeah. So that's kind of neat. Like, what's a good Pythagorean triple that I like 3, 4, 5, right? 3 squared plus 4 squared is 5 squared, right? And what else is a good Pythagorean triple? How about 1 squared plus 1 squared is what? Oh, not good. Not a very good Pythagorean triple if we're trying to keep it integer. I mean, we could do 3, 4, 5 again, I guess. What would happen then? 5, 12, 13? Ooh, yes, I also like that one. So this gives us what new Pythagorean triple? You do 15, right? Minus 48. Is that right? Huh. I guess they could be negative, whatever, right? Then what else we have? A1, B2, so that's 36. 36 plus 20, is that right? And we got 5 times 13, which is 65. What's 40? So what's this? This is minus. Yeah, we can, exactly. So we can say 33 squared plus, what we got here? 56 squared is equal to 65 squared. I mean, obviously, everybody knows that, right? So this is kind of exciting, really, if you start playing with these things. Now that's kind of interesting, right? You can continue to chase these ideas and study the structure of primes using Gaussian integers. I'll get the projector out and show you the theorem, which is known about that in a bit. But before I do that, I wanted to write something out so that you could appreciate this argument, because I think it's really neat. And probably my favorite example from all of algebraic number theory. And this is also an application of the toys we've been building here. Maybe I should do it over there. Actually, you guys, this over here, I think, hopefully, is in your DNA at this point. Yeah. All right. So here's the application. We're going to solve y cubed equals to x squared plus 2, all right, over z. Well, let's say over n, all right, via algebra in z adjoin square root of minus 2, right. Show you how this goes. This argument goes back to Euler. Not my idea. This is a 18th century thing. Now, Euler did this before any of this theory had been fleshed out. So So he was just sort of in the Wild West of mathematics, doing stuff, whether or not it was valid. And no, he's Euler. It's not quite. It's not fair. Not fair. He knew that this method had shortcoming, and Gauss was aware of it as well. And this is why Gauss didn't use the techniques I'm about to show you to prove the things he did about integers. He used modular arithmetic and more sophisticated methods. He divorced himself from the abstract algebra we're doing right now because he was aware that there were holes in the logic of the abstract algebra. It was only later in the 19th century that those holes got filled in, and Gauss's more complicated technical arguments were replaced with beautiful theoretical arguments by like Dedekind, who completed the arguments of Kummer. But here it is. So suppose if there exist x and y in n, right, such that y cubed is equal to x squared plus 2, then what could we do? Then that would mean that y cubed was equal to x plus the square root of minus 2 times x minus the square root of minus 2. See, it's this trick again. Right? And here's some claims. You can prove that x minus the square root of minus 2 and x plus the square root of minus 2 are relatively prime in Z adjoining square root of minus 2. All right. So you have the product of relatively prime things is equal to a cube. What's that say? If I have A and B are relatively prime, and I have that they're equal to like 11 cubed times, 3 cubed or something. What's that? Right? But integers. I mean, my point is, if you have that a product of two things is equal to a cube, it means that these must also separate. If A and B are relatively prime, it must be that A is 11 cubed and B is 3 cubed, or maybe A is, assuming they're not 1, of course, right? So, I mean, the point is prime factorization comes into play. So if these are relatively prime, that implies that x minus the square root of minus 2 is a cube. What that means is that you can write x minus the square root of minus 2 as a plus b times the square root of minus 2 cubed for some a and b. All right? But then what? Well, just multiply it out, do the algebra. This gives us a cubed minus 6ab squared plus parentheses 3a squared b minus 2b cubed times the square root of minus 2. So what is this? But we can equate coefficients here, right? In other words, for that equation to be true, we get two integer equations, if you will. We have, on the one hand, that x must match this, right? But we also have, it's harder to see, but there's a minus 1 right here, right? That must match that. So in other words, I get that minus 1 is equal to 3a squared b minus 2b cubed. And I also get that x is equal to a cubed minus 6ab squared. But this first equation is very nice because it says that 1 is equal to b times what? Times 2b squared minus 3a squared. Which says that either b is plus or minus 1. Now, if b is plus 1, we're out of luck. Because if b is plus 1, then this also has to be plus 1. And it's fairly easy to see that there are no solutions to that. Because you can't have 2 minus 3 work out to 1. 2 minus 3, 2 times stuff minus 3 times stuff doesn't work out to 1. So minus 1 is what we have to choose to get interesting solutions. And so that gives us that 2b squared minus 3a squared is equal to minus 1. Right? So then what? Excuse me. Well, we know b, this is actually what? This is actually 2 minus 3a squared equals to minus 1, because remember, we just learned that b was minus 1, right? So b squared is just 1. And this gives us that 3a squared is equal to 3, which tells me that, what? A is equal to plus or minus 1, right? So, completing the thought here, I don't think it actually, let's see here. I say pick a minus 1 here, but therefore, get to the point here. X is equal to, I'm gonna set a equal to minus 1. X is equal to minus 1 minus 6 times minus 1 times 1, and y is equal to what? So x works out to 5 here. Can somebody give me an argument why a can't be 1? Oh, you know what I think it is? I think that, like, so, say this. I think they come in, I think that if 1 works, then minus 1 will also work with, if I multiply this by minus 1, then that's going to change x to minus x, and this x plus root minus 2, and then over here I get, I'm not sure. There may be some reason I can't have a equals to 1. I just don't, it doesn't pop out at me at the moment.
If a equals 1, then x is negative, and he said we're doing it over n.
So if a equals 1
gives x is negative.
okay, a equals 1 gives x negative, so that settles it for us. Thank you, thank you. Thank you, that settles it. Thank you, thank you. So a has to be minus 1 then, which means that x is minus 1 plus 6, which is 5. And what's y? It's the cube root, right, of x squared plus 2, which is, by the way, the cube root of 27, which is 3. Thus, x equals to 5, y equals to 3 are the only positive integer solutions to y cubed equals to x squared plus 2. Now, something Kang said a few minutes ago is very important. Why is this calculation reasonable? There's obviously some giant holes in it at the moment. Like, I have not proved that these are relatively prime, right? I have not proved Also that there is a prime factorization that's meaningful here, right? In other words, for prime factorization to be meaningful, you must have unique factorization, right? Unique factorization domains are where dividing and conquering by looking at prime factorizations makes sense. So I'm basically using, well, this is a prime factorization, then if it's equal to the cube of something else, it must be that these are cubes. That's based on the idea that this is a unique factorization domain. This is in fact a unique factorization domain because you can prove that delta of a plus b times the square root of minus 2 equal to a squared plus 2b squared, which you would recognize from homework problem number 21, which is apparently very important. That is a norm and hence a divisor function. Consequently, z adjoin square root of minus 2 is a Euclidean domain, hence a PID, hence a UFD. And so that's why Euler wasn't wrong to do this. All right? But the larger point here is you can use this abstract algebra that we've done to actually make progress on difficult problems in number theory. This general way of thinking is called algebraic number theory, right? Let me do some show and tell for you guys here. Excuse me. Oh, yeah. It's funny how it doesn't work unless you actually plug it in. Strangest thing. Let's see here. Get my laser. So in the Gaussian integers, many beautiful things happen. A Gaussian prime, what's a Gaussian prime? A Gaussian prime is an element of the Gaussian integers which is not a product of Gaussian integers of smaller norm. That's consistent with our definition of prime. All right, but this is this definition comes from Stilwell's Elements in Number Theory, which I taught 307 out of a couple years ago. But anyway, a Gaussian prime. So, for example, 4 plus I is a Gaussian prime because if you look at the norm of 4 plus I, it's 17. 17 being prime. If you factor it, you either have 1, you have 1 and 17 or minus 1 and minus 17. Of course, 1 and 17 is the only thing that's possible because this has to be positive, and well, that means that if you factor this, one of the factors has to be a unit, right? Which is to say that this is irreducible and hence prime in this context. So anyway, 4 plus I would be an example of Gaussian prime. On the other hand, the ordinary prime 2 is not a Gaussian prime because 2 factors. It factors into 1 minus I times 1 plus I. And this has norm 4, that has norm 2, and norm 2. So this 2 is not a Gaussian prime. All right? So what's prime depends on where you are, right? 2 is prime in the integers, but it's not prime in the Gaussian integers. It's kind of interesting. There's a prime factorization of Gaussian integers. Every Gaussian integers factors into Gaussian primes. All right. And let's see if there's anything else. I don't think there's anything else particularly. This is one of the results that's kind of interesting. Real Gaussian prime. All right. So an ordinary prime, if we have a prime in the natural numbers, like 3, all right, that's a Gaussian prime if and only if p is not equal to the sum of squares. If p is equal to the sum of squares, right, that means that a plus ib times a minus ib gives us a squared plus b squared. And a plus ib and a minus ib, those are Gaussian integers which factor p in that case. And consequently, p is not prime in the Gaussian integers. So that's interesting interplay between primes and sums of squares again. Let me get to the neater theorems in here. think I have that one in the notes. We did that already. Whoa, look at that. So you can, if you start with this, you get that, and then like, I forget, I think these is, what are these? I forget what those are, but anyway. I'm sorry, there's all kinds of stuff you can do with Pythagorean triples. I must not get distracted by this. It really is not that interesting in the larger scheme of things. Pell equation, I should talk about some other time. We already talked about this. Here's the actual, like if you want to see details, if you look at my number theory, if you're interested, this is lecture, I believe this is lecture, lecture 12. Lecture 12 in my number theory page has the details of why, what I'm looking at right here. So this proves that z adjoint square root of minus 2 is the Euclidean domain. I use a geometric argument, look at the cells and argue through various geometric arguments that it in fact is a divisor function there. But I think you could also just use the fact that you've proved its multiplicative norm to prove that it gives a divisor function, so maybe that's better. Oh, but the thing is, you also need the division algorithm, and that's what this bit here helps with. And this bit of notes here also proves that I have the explanation for why I calculate the greatest common divisor of x plus or minus root minus 2 over this ring, and I show that it's plus or minus 1. Consequently, these are relatively prime, so the proof is in here of these things I claimed over there. I'm not sure they really matter too much to us in here, but in case you're interested. Now, this is more why I had this open. So to show you what goes wrong, and I think we've talked about this some before, but just to remind you again and to connect with the current discussion, if we look at z adjoint the square root of minus 3, that's actually not a Euclidean domain. Here's evidence of that in part. I've got 4. You can write 4 as 2 times 2, but you can also write it as 1 plus root 3 times minus root 3 plus 1, 1 plus or minus the square root of minus 3. And these are all primes, and these are not associates. These are inequivalent primes. And so here we have 2 distinct factorizations of 4 into primes. So prime factorization, as we usually understand it, falls apart in this ring. And so if you tried to make analogous arguments, as we did for here, over root minus 2, over root minus 3, you'd be wrong. And Euler was aware of this. And the better 18th century mathematicians were kind of aware that there was an issue here. And but you can actually fix this one by throwing in more points. So basically, you just need to make the thing kind of denser. And if you throw in these half integer points with this squiggle, this gives you what's called the Eisenstein integers, which have things like this in it, minus 1 plus I root 3 over 2. This is a third root of unity, I think. I think that's a third root of unity. And then if you throw in things like this gives you the Eisenstein integers, which is in fact a Euclidean domain. And so you can do arguments over the Eisenstein integers, z adjoin the third root of unity. You actually get unique factorization, and you can make arguments like we did over here. For example, one of the things that these are used to prove is that there are no solutions to this equation. X cubed plus y cubed equals to z cubed. There are no interesting solutions to that equation. That's Fermat's last theorem, the case n equals to 3, to prove that there do not exist interesting solutions to this. I mean, there are always solutions 1, 0, 1, right? Yay. But setting aside that, nothing, right? No integer solutions. And to prove the non-existence of this, you can do such by working in the Eisenstein integers. To see this, you can look in Stilwell's Elements of Number Theory. And so, given the success of that argument, early 19th century argument, Eisenstein, same one that we talked about in here, Eisenstein criterion, same Eisenstein. Given the success of that, that led to this character here, Lemay. He thought, well, why don't you just work with the nth root of unity adjoined to z? If you have the nth root of unity adjoined to z, then you can factor x to the n plus y to the n like this. Right? And then if this has a prime factorization, then you can make prime factorization arguments to ramp this argument up to like order n, and you can prove Fermat's last theorem. But there's just one problem. Z adjoined the nth root of unity is not a unique factorization domain. So his arguments don't work. And we have to actually go to the concept of ideals and ideal numbers to actually fix that. But maybe we'll talk more about that Friday. I just wanted to give you guys a brief introduction to algebraic number theory. I think we've done that, so I'll shut up. Thanks, guys.